So I should share my screen. So you should be seeing my screen now. I hope. Now.
Yes.
Great.
Perfect.
Okay, well, thank you very much. That was a more than lavish introduction and much appreciated. Today, what I'm going to do is I'm going to be talking about some very unusual deposits, very interesting and unusual deposits in Brazil, in the northeast part of Bahia state, in the Curaca Valley. Most of this talk was given previously at an international nickel symposium, which was a virtual event that happened through part of last year. This particular talk was given in November, and it was given on behalf of the ERO team, and the ERO team are listed on this slide here. You can see the list of names here. These are the people who are involved in that talk and in this talk as well. So I'm going to start by giving, all being well, just get things to advance. Okay, the usual cautionary and disclaimer statements, which in summary advise you to treat what I say with caution. Some of what I say will be forward-looking statements, and everything should be checked and carefully evaluated. So I'm going to start just by giving a little brief introduction to ERO Copper. ERO Copper is a relatively new company in Vancouver, been around just over almost 4 years now, and tell you a little bit about it before getting into the geology. So most of my talk is going to be geological. I'm going to show lots of pictures of rocks, which will hopefully thrill most people on the call today. So ERO Copper is a Brazil-focused company with a major operation here in northeast part of Brazil, northeast Bahia, that I'm going to be talking about today. That's the MCSA, that's Mineração Caraíba SA. So although ERO has only been around for a few years, they build on 40 years of operating experience in the Caraíba Curaçao Valley district. So they have a long operating history. They've had a major focus on exploration since coming into fruition and building up the operation again. And part of that is driven by the fact that there's a lot of existing mill capacity, excess mill capacity in the mining complex at Caraíba. So that gives them huge potential for expansion. So they currently are running about 26 to 28 drill rigs in the Curaçao Valley, and also another 5 to 8 drill rigs on their gold deposits here, the NX gold deposits up here. In the Curaçao Valley, all that drilling that's been drilling more or less at that rate for the last 3 years. So that's produced 650 kilometers of drill core. And so a lot of what I'm going to tell you about is based on that, lots of new data, lots of new observations, but very much work in progress. So brief history, ERO Copper was formed at the end of 2016, IPO'd in October 2017, and you can kind of see the growth history since that time. So initially they were focused on getting operations back into production, particularly the Pilar mine, previously known as the Caraíba mine. And then later towards the end of 2017, they got the VMEG mine also into production. They've had significant success from exploration, 5 new major near mine discoveries that are listed here on the across this bar here. Most recent one being Suriema, which I will talk a little bit about in sort of mid-2018. And that integration of those discoveries into the life of mine plan has extended that, and I'll show that in a moment. And you can see the share price trajectory, which has made a lot of people quite happy. Initially, again, their focus was on getting the operations back up and running. And so this chart just shows how they've succeeded in terms of increasing their EBITDA and particularly decreasing their debt to EBITDA ratio over those, particularly over the 3 years, 2018, 2019, and 2020. In the same process of doing all the drilling that I mentioned, 650 kilometers, they managed to extend the mine plan. So initially that mine plan came to a sort of head here 2024, 2025. And now, as you can see, it's out to 2033. And the red bars on there, I just emphasize that's inferred. That's not based on reserves yet. That's inferred and resources, which I'll talk a little bit about. And that's the deepening project, which is deep underneath the Pilar mine that I mentioned already. So that process, obviously, of life of mine extension was built around significant increases in resources. So these are the increases of resources almost 300,000 tons of contained copper added in the measured and indicated resource category since 2017. So that's been very successful, and considerable rate of conversion of those resources into reserves. This is the reserves. Again, 315,000 tons of contained copper into the proven and probable reserve estimates and so on. So it's been a very good run for Ero Copper in the last 3 years. And this is just the last sort of corporate slide that I'm going to show you, but it just summarizes kind of where they're at with the 2020 life of mine plan, which is now out 13 years. Life of mine recovery, 91.5% for copper. That's at a production rate around 46,000 tons of copper per year. Still have this very significant additional mill capacity here, which allows for further expansions. And you can see the cash cost. And then the deepening project that I referred to has the potential to add a lot more. So the interesting thing to think about, and what I want you to think about as I go through this talk, is how have they been successful? Why have they been successful? And obviously they've got a great team, great group of people working on this, both in Brazil and here in Vancouver. And they've invested very significantly in the operation and in exploration, all the amount of drilling they've done. So that's obviously a significant part of the story. But the geology has been very amenable to this. And so I want you to sort of pick up on the geology there is the rest of this talk and think about why it is that they've been able to move so quickly over 3 years to achieve what they have achieved. So we'll jump right in now to the geology. And I think this is probably what most of you are here to listen to. So we'll focus on that. I'm going to start with the regional setting. And what this map here on the right-hand side of the slide here shows is the northeast part of Bahia State. So this is Bahia State down here. And we're in this area up here, and that little box here is the same as this little box here. It's just the Curaca Valley. So this part of Brazil is complex. There's three major blocks, the Gavel, the Jacaí, and the Sarinha blocks that came together and probably collided at around 2.3, 2.4 billion years ago. The belt that runs down the center is known as the Itabuna Salvador Curaçao belt. That's the area shown in green here, through here. And that's the area of focus. So that seems to be some kind of collisional belt between these Archean belts. And it underwent, it contained some Archean age rocks and Proterozoic age rocks. And it went through deformation, major deformation events and metamorphism from about 2.35 to 2.09 billion years ago. Peak metamorphism is estimated about 2.1 billion years ago. And this is the metamorphic conditions shown here. So 850 to 900 degrees, greater than 7 kilobars. So that's at a depth of greater than 30 kilometers within the crust. And this is a really important thing that I want you to think about as I go through the talk, is these conditions of formation of the deposit are unusual for what we usually look at. Whether we look at magmatic processes or magmatic hydrothermal processes, we're usually at much higher levels in the crust. So all of the processes that you like to think about, your favorite processes for forming your favorite ore deposit, are based on relatively shallow crustal conditions. And here we are now looking at deposits that probably formed in the deep crust. And all of our preconceived ideas about how processes work need to be rethought potentially and modified to take those conditions into consideration. So that's just an interesting thing to think about. And I'll try and allude to that a couple of times as I go through the talk. At around 2.09 billion years, we have the emplacement of the Jacaré complex. That's here with the pink dot here, which is a mafic complex that contains significant amounts of chromite. It's been mined for chromite. And adjacent to it in the red color here is a very large syenite complex, intrusive complex called the Itaiuba syenite. It's over 100 kilometers long, very significant syenitic body. And that was emplaced at around 2.09 billion years. And then a little bit younger, around 2.05 billion years, we have the emplacement of some granites, pegmatites, and mafic intrusions. And that's what we're going to be interested in talking about today in terms of the Curaca Valley. So I should emphasize that these dates on which these are based are relatively limited. There's some quite good dates, but they're not particularly well constrained, and there's not a lot of them. So the 40 million year time gap that we currently have between Jacaré and the Itaiuba and the rocks that I'm going to be talking to you about today, it's about a 40 million year gap. That may or may not hold up. It may increase, but we don't know for sure exactly how well constrained that is. So bear that in mind. And the last thing I'm just going to leave you with while we're talking big picture is when I gave this talk in the Nickel Symposium, it was followed on a talk by Marco Fiorentini, who's at the University of Western Australia, who'd drawn attention to the fact that 2.09 is, of course, the age of the Bushveld complex, the super plume event that led to the Bushveld. And their belief, he and other co-workers believe you can see the effect of that super plume in Australia, assuming various plate reconstructions back into that time period, and certainly wider through Africa. And of course, Bahia State here, this part of Bahia State that we were talking about, this area in here, is pretty much adjacent to Africa. It would have originally been joined to Africa at some point pre-opening of the Atlantic. And therefore, it's not too much of a stretch to suggest that this 2.09 period may be quite significant as the distal expression of the Bushveld superplume. And you can treat that with a grain of salt if you like. That's fairly conceptual in thinking, but it's an interesting thought. Just before I leave this slide, just on the left-hand side of the slide are some of the pictures of the gneissic rocks. So these gneissic rocks have gone through at least 2 or 3 deformations. And the rocks that I'm going to talk about, mainly the mafic and ultramafic intrusions in the Curaca Valley, are coming on the end of that. So they're probably post D3, but they have seen, and therefore post or just sin to post peak metamorphism, but they have seen some deformation as well. Okay, so we'll zero in now in the Curaca Valley, and this is the Curaca Valley on the right-hand side of the slide here, and the major Pilar or Caraíba complex at the bottom here, the Melios here, which is the new mine that Era Copper brought into production in 2018, and Surubim shown here as a previous producer. All the little green blobs all through the pink in here and going up into this area here, these are all mafic to ultramafic bodies, a whole variety of different compositions, ranging from peridotite, orthoperoxenite, websterite, norite, gabbro, northosite, etc. They're dominated by orthoperoxenites, orthoperoxene-rich rocks, orthoperoxenite to norite, and that is the major host for a lot of the mineralization. But there is quite a range of compositions, and they post-date these bodies, cut and post-date therefore the fabrics and the gneissic rocks, the earlier deformation events. So the mineralization, I said, is dominantly hosted by the orthoperoxenite, and because of that association, people have often referred to these as magmatic deposits because of the clear association between sulfides and mafic ultramafic rocks. So it fits into the submagmatic sulfide box from that perspective. It is, however, copper dominant mineralization, significantly so. It's, and I'll talk about that much more, albeit it does contain some amounts of nickel, cobalt, platinum, palladium, gold, and even some of the other platinum group elements. Mineralization is disseminated to massive, dominantly chalcopyrite and bornite, and sometimes bornite is dominant, sometimes chalcopyrite is dominant, and sometimes there's no bornite. There are local zones of pyrrhotite and pentlandite, hence the nickel content, and there are also abundant oxides and spinels, so chromite, magnetite, and a range of other oxide spinels. The low nickel to copper ratio is unusual for magmatic sulfides, and these deposits also have a relatively low sulfur to selenium ratio, and that is also a somewhat unusual feature for magmatic sulfides. Similarly, the abundance of bornite is very unusual. For those of you who've worked in magmatic sulfides, you'd know that that's actually quite rare. And again, the amount of oxide that we see, the abundance of oxide, is a little unusual. So for all those reasons, some people have suggested that actually these may not be magmatic sulfide deposits. They may be some variant on IOCG, iron oxide copper gold systems, perhaps the deep roots of these IOCG systems. And that gets some support because not only do we see magmatic rocks here, but we also see abundant hydrothermal alteration across the bottom of the slide here. So we can see K, sodium, potassium, sodium, calcium alteration, and we have a lot of phlogopite associated and carbonate directly associated with mineralization. And I'll talk a little bit about that. So there's some evidence of other things going on than just conventional magmatic sulfide processes. So this remains an open question for Era Copper and for all of us who've worked so far on these rocks. And I expect you all to draw your appropriate conclusions and give me your insights by the end of this talk. And I'd be much appreciated. Thank you. Okay, we'll take a, whoops, I think I went one too far. Nope. So just to emphasize again, here's the mafic intrusions. This is the same map as the map I showed you before, but now I've just highlighted the mafic and ultramafic bodies in yellow. So you can see there's abundance of these bodies, and several of them are mineralized, not just Pilar, Surubim, and Vermelhos. There's others that are mineralized, and a lot that are under exploration and investigation at this point. As I mentioned, they do cut the gneissic fabric. So here's a nice contact between the ultramafic rocks here on the right and the gneissic fabrics. You can see that they clearly cut those fabrics. Some of the mafic ultramafic rocks are breccias. You can see here a class of different mafic ultramafic rocks within ultramafic rocks, and some form nice sort of fairly sort of normal looking cumulate type textures with coarse orthopyroxenes in a post-cumulate matrix. There are, however, some rocks which are much finer grained, like these ones here, which are range in composition from norite to gabbronorite and even to diorite. And some of these have some foliation in them, as kind of shown in this photograph here. So they're a little enigmatic as to whether they're actually part of the gneissic sequence or a late part of the gneissic sequence or part of this mafic ultramafic suite. So that's a work in progress. And I mentioned the importance of phlogopite. You can perhaps see a dark rind running up the edge of this mafic ultramafic body here, and that's a phlogopite rich zone. And these phlogopite rich zones are quite important. They occur both in the mafic ultramafic rocks and sometimes with mineralization, and I'll talk a bit more about that in a moment. But they also contain quite large amounts of apatite and zircon. So they're interesting from that perspective in terms of their origin, and of course offer something that can be dated to try and further constrain the timing of these intrusions. Okay, turning to the mafic ultramafic rocks, these are some examples are shown across the bottom of this slide here. So you can see varying composition from really ultramafic through to almost an orthositic kind of compositions on the far right-hand side. They not only vary in terms of composition and mineralogy, they also vary in terms of texture. So we have quite coarse accumulate to cumulate textures down to much finer grained, almost porphyritic styles of types of textures. So there's a lot of variation within these mafic and ultramafic rocks, and it's at this point still quite poorly understood in terms of their relationships. We don't see nice zoning, either concentric zoning or layered, layering, typical igneous layering within these intrusive bodies. Petrologically, they've been looked at by a number of researchers, and it's been further, they have a mantle origin. There's been suggestions of some alkaline signature. Some have suggested a crustal component based on some of the isotopes. Others, it's even been suggested that they are partial, the residual or restite from partial melting, although I think that's relatively unlikely. They do have elevated light rare earth elements, which is consistent with potential crust or alkaline type signatures, and they're very clearly hydrous, and I'll come back to that in a moment. The mineral chemistry is quite variable. It varies from sort of quite primitive to quite evolved compositions, both of plagioclase and orthopyroxene. And some of the particular features of the orthopyroxene are consistent with high pressure temperature crystallization, which is what we'd expect given the depth at which these are in place. So relatively high aluminum contents, for example, are indicative probably of crystallization under pressures of 7+ kilobars. There is one kind of clear analogy that many people have drawn to in terms of other areas that are somewhat similar, and that is the O'Keefe district in South Africa, which again consists of a series of mafic ultramafic intrusions placed into gneissic rocks. It's a very different age, it's about 1.2 billion years, but it does show a lot of similar features, and a number of these bodies in the O'Keefe district host mineralization, copper mineralization, including lots of bornite. So very clearly some similarities with O'Keefe. And there are a number of papers here that are listed by Wolfgang Meyer and Sarah Jane Barnes, and they are actually, to my knowledge, they're the only two people who've worked on both Caraíba or Curaçao Valley and the O'Keefe district. But that, again, almost over 20 years ago now, so a lot has happened since then, as I've mentioned, in terms of drilling and information. So if we look at the contacts a little closely now, so on the left here, we can see the contact between mafic ultramafic body and the gneissic sequence. And this is the mafic ultramafic body here is mineralized, and you can see some sulfide actually coming almost out of the mafic ultramafic rock into the gneissic ore rock. Same in this picture here, a nice contact between the two, but mineralization, which is chalcopyrite dominant here, leaking apparently, and I use that with inverted commas, apparently leaking down into the gneissic rocks. Again, a very nice sharp contact here, clearly an angular relationship between the mafic, ultramafic rock here and the gneissic fabric. And I mentioned this kind of leakage of sulfide, if you like, if that's what it is. And this is shown very nicely in this piece of drill core here with chalcopyrite dominant mineralization here and over here to the left, if I can get over there, in the pyroxenite, and the gneissic rock containing a network of bornite dominant mineralization. So it's a very nice looking mineralization, but not restricted completely to the mafic ultramafic rock. So we, as I mentioned at the beginning, the majority of the mineralization is hosted by orthopyroxenite and other mafic ultramafic affiliated rocks, but there's mineralization that is in the gneissic rocks in and around some of those bodies as well. So a couple of cross sections here, just to give you a bit of a feel to it. So on the left-hand side here is the pilar. So this is pilar located here, and this is the cross section through here. And you can see this depth here going down almost 1,500 meters now. So the deepening area that I mentioned to you previously in terms of the inferred resources and inferred additional production is down in this part of the deposit here. So this is, getting down to say 1,500 meters beneath the surface. And you can see the nature of the mineralization is quite unusual. It's more or less parallel to the gneissic fabric. Sorry, just let me get over here. Parallel to the gneissic fabric. And it's cut by a zone of pegmatitic intrusions, which are probably occupying some kind of structural feature that, in all likelihood, also controls the emplacement of the mafic, ultramafic rocks and the associated sulfides. So a very extensive vertical extent to the mineralization in Pilar, and it's still open at depth. So we have at least 1,500 meters, and who knows how far that may go beyond that. In contrast, if we go to Vermelius now, and so Vermelius is up here, and this is the cross section through Vermelius. Notice this is very different in terms of vertical extent. We've only explored the upper 400 meters, hopefully upper 400 meters of that system so far. And you can see we have mineralization which is more or less parallel to gneissic fabric again, but quite flat lying in this case, and more steeply and vertically, subvertically hosted mineralization within the zones of alteration and pegmatitic intrusions, and again, probably likely some structural association. So we're just looking a little more closely at Toboggan here, which is one of the relatively new additions to the Vermelius system. And this is a drill hole through Toboggan. And I just show this to give you a sense of the significant grade that's associated with these deposits. So this grade, which hopefully you can see here, 31.5 meters at 8.72% copper, and then a deeper intersection down here, 8.5 meters at almost 5.5% copper. So the grade is what makes these deposits extremely attractive, and this is why, of course, they've been able to add significant resource and reserve in a relatively short period of time. The other thing that's important to note here is in Vermelius, we start to see some significant nickel. So these are nickel contents. They're sporadic. They're certainly not continuous nickel mineralization, but nickel contents of up to 4.3% nickel. So that's a very attractive potential addition to the system, and obviously another target for exploration. Okay, we're going to look a little closely now at some of the mineralization, just to give you a feeling for that. So this is the copper dominant mineralization. These are examples from the Siriema and Vermelius, and you can see this disseminated to net textured sulfide texture, which is very typical of magmatic sulfides, with apparent blobs of more massive sulfide concentrated here. And you can see here there's got a sort of plaster sulfide apparently within, more disseminated material, and some kind of reaction rim that's going on around the edge of it. So that's certainly interesting and implies or suggests potential magmatic conditions. And if you look now at this picture up at the top right here, zeroing in on that, you can look closely at that and you can see very nice interstitial sulfide, chalcopyrite and bornite, between grains of orthopyroxene. And so again, this would be, most people in the magmatic sulfide world will be quite comfortable with this in terms of a magmatic sulfide texture. However, there is something that's very odd about this, and that is the distribution of the bornite and chalcopyrite. Because you can see in this slide here that they are separate, they don't occur together. There's little patches which are bornite rich, and there's patches which are chalcopyrite rich. And that's actually quite difficult to explain in terms of typical magmatic sulfide models. So if we go back just down to the bottom here from Pilar, these are more vein styles of mineralization. And you can see that they are dominated by chalcopyrite and bornite with quite unusual intergrowths and so almost fragmented textures between the two. And this is quite common in Pilar. And we see a whole host of different variations on that theme in Pilar, but not so much at the other deposits. Breccias are extremely common. So on the left-hand side here from Pilar again, you can see class of the mafic and ultramafic rock within a mixed matrix of silicates and sulfides, one breccia. In the center here, we have sulfide breccias, so sulfides with class, again, of mafic ultramafic rocks, and more of a network style of brecciation of the mafic ultramafic rocks infilled by sulfide here. We go to Siriema, and I should point out Siriema is just right here, right next to Vermelius. I'll show more pictures of Siriema in a moment. But in the Siriema here, we get into nice sulfides. Now, this time it's more pyrrhotite pentlandite rich, and again, containing clasts of the mafic and ultramafic rock. And then on the right, we seem to have almost rounded blobs of sulfide within the mafic ultramafic rock, kind of similar to the picture I showed you previously with the reaction rim around it. So we've got a range of different sulfide textures. All of these textures are quite consistent with magmatic sulfides. Certainly in many magmatic sulfide deposits, there's abundant breccias carrying silicate class, reworked material, very textured type material and so on, or taxite, it's been called by some people. So these are not out of the realm of magmatic sulfides at all, but equally well, they're not restricted to magmatic sulfides. There are other styles of mineralization which have plenty of breccias. The phlogopite carbonate I mentioned was important. So over on the left-hand side here, you can see phlogopite, almost pervasive replacement of the mafic ultramafic or noritic to orthoperoxenite rock. And again, a little bit of a reaction rim between the fresher orthoperoxenite rich rock and the phlogopitic replacement. So there's lots of phlogopite associated with these mafic ultramafic rocks. But we also see it associated with the sulfide. So here's a chalcopyrite vein, and there's a selvage along the vein here. There's phlogopite crystals growing into the chalcopyrite. And then there's a phlogopite sort of vein within the vein, if you like, cutting the vein with later phlogopite. So we have more than one phase of phlogopite introduction. And here we have some very nice coarse phlogopite integrating with chalcopyrite. And in fact, where we see it, there's no evidence of replacement between chalcopyrite and phlogopite. They seem to be in equilibrium with each other. Carbonate is interesting. Carbonate occurs as rims around some of the sulfide zones here. So here you can see there's a white material here. This is carbonate, just rimming some of these irregular sulfide blobs. And in this vein here, you can see there's a little bit of carbonate down here on the edge of it, comes out through chalcopyrite, changes to bornite, and then this is a carbonate vein that heads out here away from that. So there seems to be some relationship between carbonate and the presence of sulfide in some cases. This is quite interesting because it's very similar to textures that have been described by Dave Holwell and Darrell Blanks from the University of Leicester, who looked at a number of magmatic sulfide deposits, particularly deposits that have an alkaline or relatively primitive association. And so they've looked at some in Africa and elsewhere, and they always see these carbonate textures. And what they've suggested is that this is the carbonate is helping sulfide blobs rise in the magma and be then incorporated into the silicate melt. So I'm not saying that's what's going on here, although the textures are very similar to the rocks that Dave and Darrell have shown. And then there, as I mentioned, there is important alteration. So it's not all a nice magmatic story by any means here. On the picture on the right-hand side here, which is from Susurena, you can see these very pinking of the rocks, the nice rocks adjacent to the mafic ultramafic rocks, felspar. You can also see that the phlogopite-rich material forms quite narrow zones, which appear to be probably structurally controlled zones associated with the mafic ultramafic rocks. And again, you can see phlogopite-rich concentrations here. So we have some pretty unusual relationships both with phlogopite and then with the presence of K-felspar. Over here from Pilar, you can again see some very K-felspar-rich material within the gneissic rocks. Some of this is directly associated with pegmatites, but not all of it by any means. And then over here, this white material at Vermelius, which is more or less adjacent to, it has an irregular contact with the sulfides. This is albite-rich material. So we have sodic-rich alteration, potassic-rich alteration, in addition to the phlogopite that I've talked about previously. And so this is part of the evidence that people have used to suggest that maybe these have some relationship to IOCG deposits. And lastly, just to finish off on this story, we also have garnet that's present locally. Here's garnet over here from Vermelius. This is obviously mineralized orthoperoxenite, and we've got nice garnet developed locally. Over here, there's garnet with bornite, with interstitial to the garnet, and here we see phlogopite interstitial to the garnet along with carbonate. So it's uncertain at this point in terms of the origin of this garnet, whether this is related to specific gneissic lithologies, or whether this is an alteration product, and if it's an alteration product, how it is related potentially to mineralization. So there's a lot of questions still to be worked out in terms of both the spatial and genetic relationship of garnet to mineralization. Okay, the next 3 slides I'm going to show you are a little more detail. I'm actually going to zero into a sort of a microscopic level and just discuss the sulfide textures to give you a flavor for what they're about. And again, this is just a flavor. There's many questions as there are answers. And you've probably got that impression so far from everything I've said. Everything pretty much comes with a question mark. But these are quite interesting textures. These slides that are at different scales. There's pictures here at different scales. So I just wanted to highlight that. So the ones over here on the left, these pictures here are about 5 centimeters across. A 2 millimeter bar here, so that's about a centimeter across or so. And then these are 50 microns, so they are sort of half a millimeter perhaps across, something like that. So we have different scales. Just keep your eye on that. But they show variations on different textures, so they're quite nice to look at. So on the left side here, you can see bornite. This is from Pilar. You see bornite, again, chalcopyrite, very similar to kind of material I showed you previously. And again, here, some intergrowths between bornite and chalcopyrite. Most of the gray material in here is magnetite. So there's a lot of magnetite at Pilar. And again, when you come down here, we've got a silicate clast here. Again, bornite-rich mineralization in here, chalcopyrite and chalcopyrite bornite there. Go to a much finer scale here, you can see a very nice bornite grain associated with magnetite, and the magnetite is being partially replaced by another spinel and some chalcopyrite. And this texture is quite interesting. This unusual texture suggests annealing. So this may reflect the metamorphic conditions under which the sulfides crystallized. Just below here, again, magnetite, bornite, and this crystal here is probably melanite. So melanite is a nickel telluride. And so that's an interesting suggestion of the importance of tellurium in the system, and I'll come back to that in a moment. On the right here, we've got some digenite chalcocite. So not only do we have bornite in this system, but we also have some digenite chalcocite. And again, that's pretty unusual in terms of typical magmatic sulfides. Not unheard of, but very unusual. And lastly, down the bottom right here, this is some of that phlogopite. And the interesting thing in this phlogopite with magnetite, is that it seems to have quite a distinct fabric, and that's consistent with some of those structural relationships that I showed you of some of those phlogopite-rich zones. So this would suggest that there has been at least some deformation during and after the formation of these deposits and the emplacement of the mafic ultramafic rocks and the formation of these sulfides. And clearly, phlogopite-rich material is going to pick up the deformation more easily than some of the other units that I looked at, so that may be reflected in this picture. Okay, if we go from Pilar to Vermelius, again, same idea, different scales of observations here. So keep an eye on the scale bars here in terms of just getting your eye into what these might mean. But starting over here on the left side here, we have bornite mineralization in this area here, and above it's distinct separate zone of chalcopyrite. So this variation of bornite to chalcopyrite, it seems to be a common phenomenon. I mentioned that Vermelius has nickel and showed those nickel intercepts, and here's some quite coarse pentlandite associated with chalcopyrite and so on. And then the gray mineral that's in here and through here and all through here, that's chromite. So at Vermelius, we have a lot of chromite in contrast to the dominant magnetite that's present at Pilar. So in this picture here, we have chromite and some of that fine grained phlogopite surrounded by chalcopyrite and some bornite there. Down beneath here again, a lot of chromite, chalcopyrite, and so on. If we go over to the right, once again, we've got some mineral that we interpret to be melanite. That's still subject to be checked, but I think it's fairly likely that's going to turn out to be melanite. And again, a lot of the fine fibrous mineral here is phlogopite. And an example again of this apparent intergrowth between bornite and chalcopyrite suggests they've got some kind of crystallization history, which is exalting one from the other, or at least allowing to be integrated. And finally, again, a similar suggestion to the one I showed you previously from Pilar, with some phlogopite that appears to be picking up some deformation, suggesting that these things have seen or were in place during or have seen some deformation subsequent to their formation. And lastly, we'll go to Siriema, which is the newer discovery. It's the most recent major discovery in the camp, just along the strike, and I'll show you that in a section in a moment from Vermelius. And again, different scales of observation, but if we start over here on the left here, you can see some pyrrhotite in this case now, so more pyrrhotite than you've seen previously, and more pyrrhotite down through here. Lots of phlogopite through here, and again, the gray mineral is once again chromite, as at Vermelius. In here, some phlogopite, chalcopyrite, chromite. And then I just really want you to draw your attention to this picture in here. Now, hopefully, if you look carefully, you can see the cream-colored mineral through here, which is pentlandite, whereas the slightly browner color is pyrrhotite. Hopefully, no one's got brown-orange color blindness, but you can almost hopefully just see that. And just to see what that looks like more closely, this is like a close-up from this view here. You can see that the pentlandite is growing more or less in the grain boundaries between pyrrhotite grains. This is a texture which the magmatic sulfide people love. And for those of you, if anybody's on the call who's a magmatic sulfide aficionado, this is called loop texture. And what it suggests is that the pentlandite formed at high temperature by peritectic recrystallization from the monosulfide solid solution. So I hope you all got that. So the first sulfide to crystallize from magmatic sulfides, liquid sulfide, is MSS, monosulfide solid solution. And then monosulfide solution can separate peritectically into pentlandite and pyrrhotite. Now, this isn't terribly common. Most often what happens in magmatic sulfides is that the pentlandite exalts later at lower temperatures from pyrrhotite and forms very fine little flames of pentlandite in pyrrhotite. And that can be a problem if the flames are too fine-grained. It's a metallurgical recovery problem. So it's much nice to see coarse textures like these ones shown here in terms of the loop texture. But the other thing that's important is that if this is correct, it implies that this magmatic sulfide texture was high temperature, that it was probably formed around 800 and 900 degrees centigrade. And so that's, it certainly rules out IOCG and strongly supports the importance of magmatic sulfide kind of model. So this is an interesting kind of classic texture. But the last thing I do want to just remind you of, again, is that everything I've said about this peritectic reaction is based on shallow crustal conditions. It's a relatively low pressure. But here we're dealing with pressures which are much higher, 7, possibly 8 kilobars. And so the peritectic reaction that I'm depicted here, we don't know exactly how that would work under those conditions. And furthermore, it's quite possible that this was maintained at those conditions, and therefore it doesn't reflect magmatic conditions. It could reflect metamorphic conditions. So then we've got this complex problem of trying to decipher these two different things. And that, of course, also plays even more importantly into copper, because the copper sulfides under magmatic conditions remain liquid after the crystallization of the iron-rich and nickel-rich sulfides. And so copper-rich phases like ISS, the intermediate solid solution phase, can be liquid well down to the temperatures that I think are characterized in the metamorphism. And so they will be on the move potentially long after the other sulfides. And that may explain some of the variety of different textures that we see with chalcopyrite-rich mineralization. And again, everything I've just said is conjectural and hypothetical at this point, but it's something that has to be thought about. Last thing on this slide here, I'll just show this picture here, which again seems to look like almost an intergrowth between the silicate crystals now and pyrrhotite and chromite-rich mineralization. Okay, so I was talking just in that last slide about Siriema. So Siriema, as I say, it's a long strike from Vermelius. This is the main Vermelius deposit here. This is Vermelius West up here. And you can see we're over here. We're talking about a range here of about 2 or 3 kilometers of strike length here with these different deposits. And as I mentioned, Vermelius is known now down to about 400 meters, Siriema down to about 200. So all of this material is still open for exploration. And given that we have pilar extending now to at least 1,500 meters. That gives us considerable optimism for the future for the Vermelhos system. Just to illustrate how significant Vermelhos is, just show you a couple of nice little intersections here. These are back-to-back intersections, one here and the one next to it. So the one on the left here, this is the mineralization. Chalcopyrite rich again with coarse phlogopite. So 1 meter of 3.09% copper and 1.23 nickel. And then abuts this zone here, which has more pyrrhotite pentlandite mineralization, 1.46 meters, 7.5% copper, and 4.76% nickel. So pretty exciting, both copper and nickel mineralization in Siriema, but still a lot of work to be done to work out the distribution and therefore the potential, particularly of the nickel-rich mineralization. Okay, we're just going to wrap up now quite quickly and just summarize some of the things I've said about the sulfide textures: bornite, chalcopyrite, sometimes with digenite and chalcocite, and local zones of pyrrhotite, pentlandite, chalcopyrite. Loss of oxides and spinels, unusual intergrowths, both of oxides and sulfides, lots of variety. We've got trace minerals. We will recognize potentially melanite, there may be others. We have disseminated and net textured sulfides, which most people would interpret as magmatic. And we have complex breccias and veins. Phlogopite is important, and we have these interesting carbonate rims around some of the sulfide veins and segregations. Again, I emphasize that the mineralization is copper dominant, low nickel to copper ratio, but locally does contain significant nickel and cobalt. And then these are some of the concentrations of some of the other trace metals, and these are incomplete assays, and so we don't know the full extent of these. So everything here is under further QA/QC and analysis. So I don't want you to draw too many conclusions from these, but we clearly have some quite high silver and gold, some platinum and palladium, and then very significant amounts of tellurium, 300 ppm up to 300 ppm tellurium, 0.1 to 50 range. And there's a strong correlation between the tellurium and then copper, nickel, cobalt, and chromium. So again, that's indicative potentially of an alkaline smell to this system and a magmatic sense of that, although perhaps some hydrothermal activity as well. So conclusions, this is clearly what you're looking at here on the Curaca Valley was a pretty major metallogenic event at around 2.05. And bearing in mind the uncertainty, it may be in the 2.04 to 2.09 billion year range. We're not exactly sure yet. And I mentioned that that's an interesting time period in Earth history in terms of superplumes, magmatic processes, magmatic sulfides, and PGE. Mineralization is associated with this mafic ultramafic suite. There's evidence of magmatic sulfides texturally, but we also see some evidence for deformation and potential structural control of the mineralization. Mineralization is copper dominant, but contains these other elements that I just described. Currently, the models to explain it, if it's magmatic, would suggest that we have a source region with low degrees of partial melts. That's one way to explain copper dominance in a magmatic sulfide, because nickel tends to get retained in the mantle. Alternatively, we could have magmatic fractionation, but we don't see a lot of evidence of that. And to get to such high copper contents or low nickel contents, magmatic fractionation is really not a very satisfactory solution. And thirdly, we have the possibility of sulfide fractionation. That is, we form magmatic sulfides, and then because they're held for such a long period of time at high PT in this environment, they fractionate, and we fractionate out the iron and the nickel sulfides and separate them from the copper sulfides. So that's certainly a possibility, particularly again, given that we're dealing with this high PT fractionation. And then we have the potential, obviously, for a hydrothermal overprint on that. Phlogopite carbonate suggests that these were hydrous and potentially CO2 melts, and that at least some of that, the water CO2 was carried in those mafic ultramafic magmas. And that may have played some role in mineralization or redistribution of mineralization. We also have, and I drew attention to pegmatites and the cyanites, the Itaiuba cyanite, but we also have a number of granites, which all appear to be more or less synchronous with the mafic and ultramafic rocks. And then, of course, we have this various phases of alteration, the sodic, potassic, calcic alteration, which some people would suggest indicate IOCG processes. So that's entirely possible. Nothing is ruled out at that point that we have either overlapping or overprinting systems or one complex system that actually is a hybrid between magmatic systems and an IOCG hydrothermal system. So plenty of work to be done. So the final conclusion is probably the most obvious one. There's significant potential. I hope I've illustrated that for future resources and new discoveries. There's many of these ultramafic bodies in the belt that have yet to be explored. But we have many, many questions. So in spite of the success that we've had in the district, that Era Copper has had, there's a lot that we don't know yet. And of course, trying to improve the understanding of the district is going to be very important for further exploration. Thank you very much.
Thank you very much, John. That was great, and a whirlwind tour through magmatic sulfides, which was quite a refresher for me. Oh my goodness. Now, if you have any questions, this is to the audience, please type the word question into the chat box, and I will call on you to ask your question. And then you can unmute yourself and ask it yourself. And maybe I'll just get us started off here while people are compiling their questions. I'm just curious, John, you gave a very impartial, like a good scientist, impartial view of these different systems and the processes leading to them. Having seen the core, having been there, having worked on it, are you in one camp or the other?
I think I have 1.5 feet in the magmatic sulfide camp. So yeah, there's a lot of textual evidence that certainly supports that, but we can't ignore the questions, the things that we don't understand in the magmatic sulfide model, the things that are not adequately explained, and we can't ignore the evidence for alteration that we see. So it's an open question at the moment. I quite personally, I quite like the idea that we're seeing magmatic sulfide processes modified under high PT conditions and straddling potentially into the hydrothermal world. And of course, what that does is it opens up just a host of other possibilities. I mean, not only the things we're looking at and that ERA has discovered to date, but the potential to discover new and other different things in the belt, simply because we don't fully understand the model.
For sure. All right, we'll start with Daniel Foley.
Hi, John. This is Dan Foley from Masaba here, Text Masaba project. And I noticed you mentioned, I think it was at Pilar, you have primarily magnetite, and it's much more copper dominant mineralization. Whereas at Bermeos and the third one, which I can't remember the exact name of, it looked like maybe you had slightly more nickel rich ore and that there were also more chromites associated with those. Is that an association that you commonly see?
So based on what I showed and what we know, yes, is the answer. Yes, so Pilar is copper dominant with chalcopyrite and bornite. Vermelhos Siriema, which is the other one you mentioned, has more nickel. We don't know yet how much, but certainly has more nickel and more pyrrhotite-rich mineralization and less bornite. And yes, based on the relatively limited information to date, it appears to be more chromite-rich at Vermelhos Siriema and more magnetite-rich at Pilar. Pilar is definitely magnetite-rich. Less certain about the amount and distribution of the oxides and spinels at Vermelhos and Siriema.
Does that seem to occur just at like the prospect level, or is that at the sample level as well? Because I know you said nickel mineralization seems to be really spotty even amongst certain holes. Do you get higher chromites in specifically nickel-rich samples, or is
Don't know.
Prospect scale? Not.
Don't know. So I mean, lots of great questions and lots of things to be pursued. There's just an abundance of variation. So I think everything I said, you should assume there's variety, and we don't fully understand yet. So that's all ongoing work in progress. The ERA team is busy looking at all these things. And given the amount, as I mentioned earlier, that they've drilled, there's a huge amount of observational and geochemical other data that's being incorporated continually in the understanding of the deposit.
Thanks, John.
Great, thanks, Dan. And on to you, Dave.
John, yeah, thanks for the talk. It's probably it's a long story for each of those discoveries, but I'm just curious on the actual discovery and how they were. Is there a common thread that links the discovery stories together? And then kind of a related question is, do you have a way to differentiate between all the other intrusions? You seem to have a no shortage of targets there, and what makes one potentially more prospective than the other?
So the second part, great question, work in progress. Some ideas, lots of ideas, but nothing that's definitive yet. So the exploration, and I think there are other people on the call here from the ERA team who could actually probably comment more on this, but the exploration was both a product of existing knowledge. So there was a lot of existing knowledge based, you know, I said there's 40 years of history in the belt. So some of these targets were existing, known or well-defined, and then new discoveries, which is a combination of step out and combination of geophysics and geochemistry. So it was, you know, soil geochemistry at surface, and then obviously drilling information and geophysical signatures. So a combination of different signatures and characteristics that have been used to target different targets.
Good, thanks.
No, sorry to not give you simple answers. It's not a simple place.
Thanks, Dave. Neil, you have a comment. Do you want to unmute yourself, or otherwise I can ask it? You go for it.
Okay. Hey, John, that was awesome. One thing that's also going on at the time, at least in the background, is the Trans-Amazonian, right? Which equivalent to the Trans-Hudson for those less familiar. So I think what did I write down? Could the formation of these mafic, ultramafic bodies represent localized changes in the tectonic regime from compression to extensional during the evolution of this district? And then the CO2 associated with that, everyone's talking about those sort of volatiles and extensional regimes, right? So what could that rifting, is that rifting manifested anywhere else?
So the answer to the first question is, well, actually the answer to all three of your questions is yes, yes, and yes. I mean, yeah, it could well be at the end of the stage of compression. We're definitely the end of compression and peak metamorphism. So have we gone into extension? Possibly. Is it, relaxed? We're beginning to relax, introduce melts into the deeper part of the crust here. Definitely possible. Is it part of the Trans-Hudson? I mean, Trans-Amazonian? Yes, maybe. Could it still be related to bushveld? Yes, maybe. What else do I need to say yes to? Yeah, I mean, it's just a fascinating combination of things that are happening at that time, both in Brazil, but in other parts of the Proterozoic, and how they all fit together, and what this is telling us in the bigger picture is just a great question. But we're focused on the exploration, so we're not addressing it at that scale, but there's lots to be done there. And I can see here that the ERA people are sitting next to the pool in Brazil, waving to us. So if they want to add a comment on exploration, we should get them to pipe in and say something.
I mean, that was actually going to be my next question about exploration. I saw the long section, and was it correct that there were 20 plus rigs, or there are 20 plus rigs in action?
Yeah. 26 to 28. Yeah. So
that's insane. So where's the focus in that long section for this year?
So some of those are underground rigs, obviously. So working in the deepening zone. So there's a big focus on the deepening zone and the other. But I'm going to let Pablo. You just unmuted. So Pablo, perhaps you could jump in here.
Hi everyone. This is Pablo Mejia, VP Exploration at Orocoper with the other team of Orocoper. So that's right. You can hear me?
Yep.
Okay. So just a reminding, that initial image that John shared at the beginning is 100 kilometers, and we have three main districts, and we have a lot of drilling in those two main districts, Vermelhos and Pilar. And as John said, a lot of those drilling is focusing in underground and extending or expanding the resources, but we have a few places that we are drilling in the regional program. And just replaying one of the questions about the exploration, we have three main of the stuff that work very well here, and it was part of the discovery of Siriema. One is ground gravity to identify the mafic ultramafic that works very well as a first pass. The other is IP, works very well to identify the chargeability on those places that may be showing sulfides. More recently, since Orocoper is working, we are working more with Borjo EM. That was one of the tools that you use to discover Siriema and the rich part of Siriema with high-grade nickel. that works very well because that pentlanded pyrrhotite association is really well identified with the borehole EM. We have a big plan running right now, but we have historic data in soil geochem. And as John mentioned, cobalt, copper, chrome, nickel work very well an association to identify that the mineralization, main mineralization places, and we can see that signal through that combination on both sides and in Vermelhos and Pilar, and also in other places that we are trying to follow in the exploration in regional. So I don't know if I answered that question, but
That's great. Thanks, Pablo.
That's great. You answered it and more. Are there any other questions from the audience here before we wrap up?
Could anybody just explain it to me?
That's free consulting. I don't know about that. MEG's next venture.
John, I don't seem to be able to get you on my chat, but can you hear me?
Yep.
I just wanted to know two questions. What metamorphic grade do you think these things have? They're 30 kilometers depth. And the other thing is, do you have any composition data on the garnet?
So granulite conditions,
Okay.
certainly pre-emplacement of the Mayford, the gneiss were at granulite conditions. So they even contain sapphirine in places. So we're up, as I said, in 800 degrees and possibly 7-8 kilobars. At the time of emplacement of the Mayford bodies, we're probably post that, but we don't know by how much. I doubt we're very much different. I suspect we're more or less under those conditions at the time. And no, we don't have garnet compositions yet. I mean, there is just tons to do in terms of mineralogical control, mineral chemistry, and so on. We're doing a lot, observational work already, and there is some data because there's been quite a lot of research done over the years by Brazilian researchers in the belt and others. And so we have a lot of that, but there's just been such an expansion of information in the last 3 years. There's just a lot to do.
Thank you. It was a great talk. Thank you very much.
Well, I couldn't agree more. And I think on that note, we will wrap up for today. John, thank you very, very much for your time and a really, really great technical talk as well. And a great introduction to me to Arrow Copper. So thanks to all the exploration geologists for joining us as well. And just a note on our next talks, depending on how you heard about this one, just make sure that you visit the Vancouver MEG website and subscribe to our email list so you can hear about future events. We're also on LinkedIn under Vancouver MEG, and so you can follow all of our events. And a copy of this presentation will also be available on our website. So John, I welcome you to stay on while people sign off for a chat. But thank you to everybody for joining us, and a big clap for John today.
Thanks very much.
See you next time. I think I saw Anne was online too, was she?
She was. She's just across the hall from me.
Oh. Yeah, that's great.
Yeah, that was good. Great turnout.
That's good.
Superb turnout. I mean, great for the start of the year as well. Start off with a bang. We found that I mean, exactly as we were talking about, we definitely have more people joining virtually than we do before. And it's funny because there were how many people from Arrow Copper? 6 or 7 gathered around there as well. So you see people gathering in groups too, which is really good.
Yeah, no, they're a great team.
And when were you down there last?
I haven't been down there for a year.
Oh, okay. Well,
yeah.
Of
so
course,
the team's down there now, and so I think the team from Vancouver is their second time down since March. So yeah, it's been. I mean, there's a great group of people. The Brazilians there are obviously great people, and they're doing terrific work. But it's difficult still doing everything remotely, and with that amount of work going on, it's tough. 28 drill rigs turning, And then there's an equivalent amount of work going on operationally in terms of optimizing the operations and so on. So, Anthea Barth, who looks after that for Aero, is just doing an amazing amount of things in a very short space of time.
Seems like it would be a great PhD project, or 5.
Yeah, I'd say 5, 10 maybe. So there is a master's student who started, who was listening in, Tercio Nunes, who's a Brazilian. He's at Queen's now working with Gemma or Olivo. So he's just started, so he'll look at Vermelhos, but that's a master's project and a complicated master's project, but he'll look at some of the mafic ultramafic rocks and so on at Vermelhos, but that's just scratching the surface. So we're busy right now, talking to a lot of researchers. There's a lot of interest, and there's some great people in Brazil, some who've worked there previously, and we're just trying to work out how to use them appropriately. And then we've got other people. When I presented to the nickel sulfide symposium, there was a lot of excitement amongst certain people on that call. And I didn't say this on the call. I don't know who's left, but this is extra information you're just going to get from me. One of the things that several of them noted was similarities to Nova Bollinger. So if you know Nova Bollinger's nickel copper deposits in the Fraser Belt in Western Australia, and also placed at relatively high PT conditions. And some of these sulfide migration and melting textures that they see are very similar to some of the things that I think we're seeing too. So that's kind of an exciting possibility to draw in some of the CSIRO and other researchers from WA into this as well.
Absolutely.
John, thank you very much. Yeah, I'm one of those post-presentation person. Yeah, exactly. No, first of all, thank you so much for such a great talk, John. It was an eye-opener for me. Didn't realize that we can have such a diversity and variety in the magmatic to hydrothermal continuum. And it was fascinating for me to see those structures. I think there is a lot more structural affinity to that valley also, that zigzag pattern. Reminded me of some sort of trans-tensional tectonic stress regimes, like Neil touched base on that. And the looks like there's at least 2 compression and extensional stress regimes involved in the development of this mafic ultramafic complex. I was wondering if they have done any VTEM survey also, like airborne throughout the valley for future exploration follow-up.
Yeah, well, there's airborne magnetics and some previous EM work and so on. Yes.
Okay.
Yeah.
Well, that's quite exciting.
Yeah, no, it is. It's just a fantastic place to work, but it is a very challenging place to work because so many of the textures and things you look at on a day-to-day basis are difficult. They're not easily categorized or classified and so on. So,
but I would agree with you. I would agree with you that 70% of magmatic affinity when I looked at those net textures and loop textures, and I think there's a lot more magmatic.
It's pretty hard to argue with that unless we've got the loop texture completely wrong. And there's some pretty good information on that. Yeah.
Awesome.
Good. Anybody got me a last question before I go have my lunch? Anything else you'd like me to answer?
Is there any ophiolites in that belt, in that area?
None that I know of, no.
Okay, so they're pretty much intact.
Yeah, the Jacariki complex that I mentioned, which is a mafic ultramafic complex, has chromite, but it doesn't look to be ophiolitic. At least no one, I've not looked at it myself, but nobody that's looked at it has interpreted it as ophiolitic to my knowledge. It seems to be an intrusive complex. And so, it's very interesting. It's not that far away. And the other thing I didn't mention is there's another nickel sulfide deposit further it's quite a long way to the south, Santa Rita. And that's the same age. That's again 2.09. So there's definitely something fairly important going on at that time in Brazil as well as in Africa and other parts of the world. That's the big picture.
Thank you, John.
Okay.
All right, John. We'll let you go. Thank you again. And I promise if you do another talk for the Vancouver MEG and after COVID, you'll get your bottle of wine. But not this time. You missed out.
I have lots of other things I'm willing to talk about. If you're ever short, just let me know.
That's good to know.
Okay.
Thanks again. All right. Take care, everyone. Bye,
Yeah.
John.
Take care.
Bye.